Just a second here.
While we're waiting for that, I want to mention the co-authors on this paper. Dr. John Santarius from the University of Wisconsin, Dr. Jack Schmidt, who is adjunct professor at the University of Wisconsin, and Mr. Aaron Olson, who is a graduate student at the university. The talk today will probably be a bit orthogonal to some of the talks you've heard, in the sense that we're talking about nuclear processes, and in particular the isotope helium-3 and its importance and benefits to lunar exploration. This is a project that we started back in the mid-1980s, and so it's not a brand new one, but it's one that we keep finding more information about. So we're ready to go?
Yes, and you can control the advancing with the arrows at the bottom.
Okay, got it. In the 70s and 80s, we at the Nuclear Engineering Department at the University of Wisconsin had spent a lot of time, an effort working on deuterium-tritium fueled thermonuclear fusion reactor designs. And we had since then published on the order of 50 magnetic fusion facilities, at least designs of those. And we recognized in the process of those reactor designs that there were major problems associated with the 14 MeV neutron that's emitted from the DT process. These are just a few pictures of some of the reactors that we designed in the early time period, that is the 70s and the 80s. The motivation for looking at helium-3 as a fuel instead of the deuterium-tritium, that we decided that advanced fuels were needed to reduce the level of radiation damage and neutron-induced radioactivity. Out of the somewhat 35 to 40 fusion fuel cycles, 3 of the top 5 that are the most efficient cycles are relatively free of the damage and radioactivity issues that come from the release of neutrons. And of course, 2 of these cycles are based on helium-3 as a fuel. Just as a quick background, I'm not going in any detail here. These are the 4 cycles that are being used around the world. Actually, the first one is the one where most effort is on, and that's a combination of a deuterium and tritium atom, which releases 80% of its energy in 14 MeV neutrons and a helium particle. The DD reaction, which has a branching ratio, one of which releases a neutron, the other releases a tritium atom. And those top 2 are the main cycles that are being pursued around the world today. But both of them involve large amounts of neutrons that are emitted during the radiation or of the fusion process. The third cycle, deuterium and helium-3, as you see, only releases a proton and a helium-4, but there are a few neutrons that come from associated DD reactions. And finally, the last one is a helium-3 reaction, which only releases non-radioactive materials, and we'll come back to that in a minute. To illustrate the importance of these 2 cycles, I've put together this plot which normalizes the amount of neutrons that are emitted per kilowatt hour released from the fuel. And we normalize that to fission, which is, we'll call 1 in this case. And what you see is to produce the same amount of kilowatt hours, we release 5 times more neutrons in the DT reaction, and on the order of 10 times more neutrons per kilowatt hour from the DD cycle. And those of you who have done anything with nuclear reactors know that the large number of neutrons is a nuisance, and in some cases it's fairly debilitating to the materials of the reactor. If you move over to the D-helium-3 reaction, you see that number is reduced dramatically down to 0.04 or up to 0.2, depending on how we handle the tritium that's bred. And the helium-3 cycle actually has no neutrons associated with it. So you can see why we were interested in the 2 reactions on the right side, because they release far fewer neutrons or none at all. If we go to looking at the characteristics of the D-helium-3 fusion power plants. Obviously, no greenhouse gases or acid gas emission. Very high efficiencies because we work with a direct conversion of the ions. Greatly reduced radiological hazards. It's hard to get a very precise quantitative number, but it's on the order of a factor of 10,000 reduced from a fission reactor. There's no high-level waste, for example, that you'd need to store in a facility like Yucca Mountain. And probably the most important thing is that there's no possible off-site nuclear fatality in the event of a worst possible accident. That would be a hurricane in the middle of an earthquake, so that everything would be released to the environment, and even if it was, it would not result in any fatalities. If we look at a helium-3 fusion power plant, we have the same advantages in terms of greenhouse gases, very high efficiencies, but in this case, there would be no residual radioactivity, even after 30 years of operation. That would mean no nuclear waste or nuclear safety hazard. And of course, what that means is that we could actually produce nuclear energy without nuclear waste. And it sounds rather unbelievable, but in fact, you could do that if you could make that fuel cycle work. So that's why we were interested in helium-3. If we next look at what has been going on in the fusion of these fuel cycles, on a small scale, we've demonstrated the fusion of deuterium helium-3 in devices at the University of Wisconsin, first in 1999, and then later in 2006, we demonstrate the fusion of helium-3. I would very quickly caution, though, these are a long way away from break even, and obviously much bigger facilities would be needed to produce electricity. But as a proof of principle, we've already done that. The helium-3 is a well-documented resource. You've probably heard a lot about that during this conference. In 1986, we published the first article connecting the Apollo discovery of helium-3 to the fusion program, and that, to our knowledge, was the first time that people had made that connection. As you know, the helium concentrations have been measured, helium-3, from the Apollo program and actually from some of the Russian Luna samples. The analysis indicates, at least on an order of magnitude, that there's about 10 to the 9th kilograms of helium-3 in the near surface region of the lunar surface deposited by the solar wind. And if we were to convert that into energy, that would be about 1,000 years of world energy supply. 40 tons of helium-3 would supply the needs of the entire U.S. electrical needs in 2012, and 10 kilograms would produce about 200 megawatt years of fusion energy, and that's the amount of helium-3 we have on the Earth right now. Most of it's being used by Homeland Security. And of course, if we went to the gas giants, there's quite a bit more that one could use if we ever ran out of the helium-3 from the moon. We've designed several miners starting in 1988. The Mark I facility moved to a little bit more detail in Mark II in 1994. Most recent design is a Mark IV design in 2006, and we're ready to work on Mark III is 2006. We're ready to work on Mark IV. The table here is for your information on details of the miner performance of Mark I and Mark II. The near-term mining focus that we're working on now is a demonstration of a small miner that produces important volatile byproducts and tries to show that you can extract those, and it's scalable on the surface of the moon. We're focusing on the volatiles themselves, but they could also be used to detect creep and other materials on the moon. The process for extracting helium-3 is fairly straightforward, and we won't go into the details here. It's all outlined in a lot of papers. But if you normalize everything to per ton of helium-3 extracted from the surface of the moon, you find that there's about 18,000 tons of other things that will come out from that 1 ton of mining helium-3, ranging from hydrogen to water to nitrogen, carbon compounds, and of course other helium isotopes. Here is another table that is for your perusal later, but I would point out the only thing that we were interested in on this particular table is the amount of water that would be needed for crew members, and we used the amount of water delivered to the space station in 2012 as sort of a minimum, and that it turns out to be about a kilogram of water per day per crew member. But of course, that relies on a lot of recycling of water in the space station, and on the moon it might not be quite as good. At least that gives us an order of magnitude how much water we need. We've also then looked at trying to show what a small miner, like a official one that would be designed that could produce about 100 grams of helium-3, that would actually produce about 320 kilograms of water, which would be enough to support one crew member for a year. As you move to the right, you can see that mining about a kilogram a year would result in about 4 tons of water and support a crew of 12 in a Bigelow Alpha station. And way off to the right, of course, is what you'd see from a commercial miner, where we would actually be providing helium-3 for a fusion power plant.
You have 90 seconds left.
How much?
90 seconds.
The significance of the lunar helium-3 is that 1 ton of helium-3 can provide the annual electrical needs of 10 million Americans, and 40 tons of helium-3 could provide all the electricity used in the United States in 2013. At today's oil prices, about $100 a barrel, that would make the energy content in a ton of helium-3 worth about $5 billion, or if we use one of the former U.S. shuttles, they would have a payload of nearly $100 billion. So the conclusions are that the moon could actually become the Persian Gulf of the 21st century if fusion reactors burning helium-3 can be commercially built. Secondly, early missions can demonstrate that extraction technology and provide lunar volatiles for life support for initial lunar exploration. And finally, fully developed helium-3 mining activities could provide large quantities of life-supporting volatiles for lunar bases, space exploration, and act somewhat, the moon could act somewhat as the Hudson Bay store of the latter 21st century. So with that, I'll close and answer any questions. Thank you.
Thank you very much, Gerald. I think this was a fitting end talk to see what kind of future we might be able to get and the enormous benefits that might be out there. I've had a number of talks with Jack Schmidt about this. I know he's been a huge proponent as well for quite a few years. And let's see, I'm not seeing any questions there, so I actually, okay, Pam's typing, but I actually have some questions to start out. First of all, what is the naturally occurring ratio of helium-3 to helium-4? How rare is it, at least on Earth? I know you gave an amount, but I'm curious about the ratio.
Well, of course, the lunar helium-3 would come from the solar wind, and whatever the fraction is there, and it's about 100 parts per million. It, of course, varies on Earth because a lot of it gets diluted from the helium-4 that comes from uranium decay inside the Earth. So as helium accumulates in gas deposits on the Earth, depending on their proximity to a uranium deposit, that number could vary down to a much lower level. More like 1 to 2 parts per million.
Okay.
Most of the helium-3 that's available on the Earth, though, comes from the nuclear weapons program, from the decay of tritium in our nuclear weapons. We, at one time, had about 30 kilograms of helium-3 available on the Earth from the United States, and some from Russia, of course, additional, now some from China and France. But most of that now has been diverted for homeland security issues, and there's less than 10 kilograms available now. And that's going probably to zero very quickly. And the price has gone from, originally when we started this work, $1,000 a gram, to currently it's about $7,000 a gram, and projections are that we'll go to about $30,000 a gram in the near future.
Wow, wow, amazing. We have a question from Pam Clark. Can you envision such a concept using standardized small sat platforms traveling to and from Earth on low delta V trajectories with minimum fuel expenditure?
Sure. Helium-3, of course, is stable. As long as you got it coming back, it's not too important to have it come back in a very rapid fashion. And there have been several ideas on how to get helium-3 back. Obviously, you wouldn't send anything else back, no water, no helium-4 or the other issues or other materials. So, yeah, I think there's a lot of room for very innovative ways to get the helium-3 back to the Earth, and time is not really the big issue.
Okay. Another question I have is, would you expect a homogeneous distribution of helium-3 on the Moon, and if not, why not?
Well, there are two comments to that. One is that there seems to be an association of helium-3 with ilmenite, and we don't know why, and that's a good research area. But that does seem to be at least empirical evidence. The other is in the depth distribution, and I think the Apollo program went down 1 to 2 meters in terms of their cores, and found that the helium-3 in the mare of the Moon was fairly uniform down to 1 to 2 meters in the pulverized region, of course, of the mare. So I guess to answer your question, it would depend laterally, or in 2 dimensions, somewhat on the mineral content, and ilmenite seems to be one of the favored areas. And depth-wise, it looks like it's fairly well mixed or gardened in the mare of the Moon.
Okay. And I had one last question, and that's regarding reactor design, because I know we've spent over 50 years looking at reactors designed for deuterium-based processes, and what would you estimate the difficulty as with helium-3 based processes? Well,
the big advantage of helium-3 is that we wouldn't have to develop radiation-resistant materials, and that is a big part of the current fusion program, which has not been identified yet, or not, at least not in a big way. Most of the effort has been on the plasma physics. So that would save a lot of time for commercialization, even though the physics is somewhat harder. There are private concerns in the United States, and there may be some outside the United States now, working on the use of advanced fuels. And there is a company in California that is looking at this, and we know the Chinese are very much interested in this area. Russians have been interested in the past 2 years, so that it's truly an international interest. But there's not a lot of public information on that. Tri-Alpha Engineering is one of the companies in the United States, not necessarily looking so much at helium-3, but T-boron-11 and helium-3.
Okay, all right, well, thank you, and thanks again for an excellent talk, and I'd like to have one more thank you to all of the speakers in this morning's ISRU session.
Good job running it, Greg.
Oh, thank you. It was a lot of fun.
And before we